Welcome to Red Dragon Mission Training. Training number 4, Newton's Laws. This video tutorial will cover the following learning targets. Work towards mastery by answering the questions and example problems. Newton's 3 laws help to explain how and why most observable motion happens. Newton's first law is stated, an object at rest tends to stay at rest. An object in motion tends to stay in motion. That is, until an outside unbalanced force acts on it. A soccer ball doesn't want to move until you kick it, applying an outside unbalanced force. A hockey puck sliding on the ice doesn't want to stop unless it hits a wall. It's applying an outside unbalanced force. Newton's second law applies mostly to acceleration, so we're going to skip over to Newton's third law. For every action, there is an equal but opposite reaction. When you push on the ground pushes back with the same exact force. Right now, the Earth is pulling on you, but you're also pulling on the Earth. A force is something that pushes or pulls. This is why objects move. It's because forces are acting on them. For example, you move forward or backwards depending on how you push along the ground and how the ground pushes back on you. Forces can be broken up into different categories based on what is causing the force. If your object is sliding across a surface, it's causing friction. That kinetic friction may slow the object down. We symbolize the force of kinetic friction by F sub Kf. So this is a force acting opposite the motion of the object. This is a ball rolling forward along the ground. Friction slowing it down by acting against it. If friction is so strong between the surface and the object that it stops, we're looking at static friction. In this case, the force acts opposite of the likely motion. If something is sliding down a hill, but it stops, the force of static friction is acting against the direction it's traveling down the hill, keeping it in place. Friction forces can also be represented simply as F sub F. The gravitational force can be represented by F sub G. These forces always act straight down into the earth. Applied forces are forces applied in any direction described. So this is objects being pushed, pulled, kicked, hit. If it doesn't have a specific force, applied forces, or F sub A, is a really safe category. If the force is being applied by a string or rope, we call it a tension force, F sub T. If the force is being applied by a surface, it's a normal force, or F sub N. So any object sitting on a surface, a person sitting in a chair, a plate sitting on a table, those have normal forces. The plate is pushing down on the table is pushing up on the plate. These forces are always applied perpendicular to the surface. When forces interact on an object, they can push and pull in opposite directions. Sometimes this can create balanced forces, where the forces are pushing and pulling with the same amount, or creates unbalanced forces. Balanced forces and unbalanced forces create different types of motions. Constant velocity is caused by balanced forces. If an object is stopped, its forces are balanced as well. If an object is speeding up or slowing down, we have unbalanced forces. That means one of the forces is pulling or pushing more than the other. A force diagram is a visual way of showing all the forces acting on an object. To draw a force diagram, we represent the object with a large dot. Each force is represented by an arrow. The length represents the relative magnitude, so the relative size. A bigger force is represented by a longer arrow. These arrows represent the direction in which the force is acting. These forces always act away from the object. Forces can act vertically or horizontally. If forces act on an angle, we need to break down the individual components of that force into vertical and horizontal components using trigonometry. The direction should always point away from the object. If you're pushing a cart, the force may feel like it's going into the cart, but it's pushing away from the cart. You're transferring that force through it. For example, an object is pushed along a surface to the right, causing friction. In this case, the arrow represents where I would be pushing the box. However, that's not the way the forces will be drawn. Start by representing the object, in this case the box, as a dot. Ask yourself which forces are present. The object always has gravity. All objects have gravity when we're drawing force diagrams. Gravity always goes straight down. Is this force vertically balanced or unbalanced? Well, vertically, that box isn't moving up, it's not moving down, so it's stopped. That means I need to balance out that gravitational force. It's on a surface, so I need to balance it out with a normal force. As I draw my diagram, I label the name of the force. I need to know what's causing this motion. I'm pushing this box, so I'm applying a force. That's F sub A, my applied force. It's causing friction because it's rubbing against a surface. If we assume it's moving at a constant velocity, since it doesn't seem to be accelerating, that means we're going to have balanced forces. The object's moving as it rubs against the surface, so it's going to be kinetic friction, F sub Kf. Knowing how these balanced forces relate to one another can help us find unknown information later. To write a balanced force equation, you must always start with a force diagram of the motion. Are the forces balanced or unbalanced? If they're balanced, write the forces that are equal to one another in equation form. Up balances down, right balances left. So vertical forces balance each other and horizontal forces balance each other. Let's look at the example of a car driving at a constant velocity. I'm going to start with a force diagram. There's my car. I'm representing it as a dot. Gravity's pulling down, F sub G. It's not accelerating up or down, so I assume vertically it's balanced. It's on a surface, driving on a road, so it's F sub N. The normal force is caused by a surface. The car is driving to the left, so I'm going to apply a force to the left. It's driving at a constant velocity, which means horizontally those forces have to be balanced. Fa is applied to the left, left balances right. What force acts against motion? It's always going to be friction. And since the car is moving, it's kinetic friction. Look at the way these forces seem to line together. Gravity often opposes normal forces. Applied forces often oppose friction forces. It's not always the case, but if you start looking for the trends in the force diagrams, things will become a lot easier. Now we need to look if these forces are balanced or unbalanced. I drew all these magnitudes exactly the same. The green arrow going down is the same length as the green arrow going up. So they're the same velocity, or same force. Same thing with the left and right. So vertically and horizontally, I'm balanced. So I'm going to write Fn equals Fg. Those forces are balanced. That means if I knew my normal force, I'd know my gravitational force. Fa equals F sub Kf, so my kinetic friction force is equal to my applied force. If I knew my applied force, I would know my kinetic friction force. If by chance my applied force wasn't as big as my kinetic friction force, so in this case I would be slowing down. I wouldn't be at a constant velocity. Fa does not equal F sub Kf anymore. My only balanced forces in this equation are my vertical forces. Not all forces are balanced or equal. A hockey puck moves at a constant velocity without friction. Draw the force diagram, establish if the forces are balanced or not, and then create force equation or balanced force equation. The puck has gravity, the surface or the ice is pushing up, but nothing's pushing it. It says constant velocity, so horizontally I know it has to be balanced. 0 equals 0, so horizontally we're balanced. Vertically, since the puck isn't accelerating up or accelerating down, we have to assume it's balanced in all directions. Fn equals Fg. Even though my horizontal forces are balanced, they are non-existent. Understanding balanced force equations helps us to quantify or add value to force diagrams. Quantitative force diagrams are force diagrams with direction arrows, labeled forces, and numeric magnitudes. Some forces can be calculated using formulas. Other forces must be inferred using force equations. So in this case, I have a force diagram. I know my normal force. I know my friction force. I know that Fn equals Fg, Fa equals Ff. So if I know that Fn equals 2.5, Fg has to equal 2.5 newtons as well. If I know that Ff is 3 newtons, then I know that Fa is 3 newtons as well. Some forces can be calculated using specific equations. Gravitational force is usually the first force you're going to calculate. It's always the first force that you draw on your force diagram. It can be calculated by taking 9.8, which is the gravitational force constant for the Earth, and multiplying by the mass in kilograms of the object. If I'm trying to calculate friction forces, and I know whether, it doesn't matter whether they're kinetic or static, if I know the normal force, I just have to multiply it by mu. That's that fancy looking m. Mu is the coefficient of friction. It's a unitless value that describes how much two materials stick to one another through friction. A mu closer to 1 sticks more. A mu closer to 0 slides more. Ice is closer to 0 on the mu or coefficient of friction scale. Let's draw a force diagram for this example. I have a box that's 4 kilograms on a surface at rest. I know there's gravitational forces involved because there always is. It's on a surface, so I have a normal force. The object isn't accelerating or even moving left or right, so there's no horizontal forces. It's not accelerating up or down, it's at rest, so these are balanced forces. If I wanted to quantify this, I could calculate my gravitational force. The formula to find the gravitational force is 9.8 times the mass. So that's 9.8 times 4, which is the mass of the box. That gives me 39.2 newtons. Newtons, again, is the unit for forces. Label that value right into your force diagram. F sub g equals 39.2. If I know that the gravitational force is 39.2, that means I know the normal force is also 39.2 newtons. Newton's second law describes motion that's accelerating. It's not a phrase, but a formula. The net force equals mass times acceleration. The net force is the change or difference between opposing forces on an object. It's how much more a force is pushing in one direction than it is in another, or how less it's pushing in one direction than another. This formula and the gravitational force formula help us explain why 9.8, the gravitational force constant, is a variation of acceleration. If an object accelerates, it has a net force. That means something is pushing or pulling more than something else. One force is bigger than another force. If a net force acts on an object, it causes it to accelerate. This is how we break out of Newton's first law. An object at rest wants to stay at rest. An object in motion wants to stay in motion unless acted upon by an outside unbalanced force, which causes acceleration. Let's try an example together. The Falcon Heavy rocket and its payload have a mass of 1,407,200 kilograms. The Falcon Heavy rocket can provide 20,418,000 newtons of thrust during takeoff. What is the net force during takeoff? I need to start with a force diagram. I'm going to represent the rocket as a dot. Gravity's pulling down on it. However, I know that it has a lot of thrust pushing up. Some force values are given to you in the problem. In this case, I know that the rocket applies 20,418,000 newtons of force upward. This is what causes the rocket to accelerate. I need to find the gravitational force acting on the rocket by taking the gravitational force formula, 9.8 times mass. So I'm going to take 9.8 times the mass of the Falcon Heavy rocket. That gives me a total of 13,790,560 newtons. Now that I have both forces, I can find the net force. I can find the difference or change between these forces. The forces pulling up are pulling more than gravity's pulling down. So I can subtract them to find the difference. The net force equals the bigger force minus the smaller force. 20,418,000 minus 13 million and change. That's going to give me a change or a difference of 6,627,440 newtons. That extra amount of force is pushing up. That means that the rocket is pushing with 6 million newtons more than gravity's pulling down on it. These unbalanced forces cause the rocket to accelerate. If I wanted to find the acceleration of the rocket, now that I know the net force and the mass of the rocket, I can use Newton's second law. F net equals m times a, or mass times acceleration. I'm going to plug in the information I know, the net force, or the change in force, the mass of the rocket, and I'm solving for acceleration. This is really turning into a one-step equation. What's happening to A? I'm multiplying by 1,407,200, so I'm going to divide by that value on both sides. My acceleration is 4.71 meters per second squared, which, if we think back to our understanding of acceleration, is a reasonable answer. The rocket's moving up in a positive direction, and it's changing velocity in a positive direction. It's increasing its velocity. On your own, try to complete this problem. The Falcon Heavy is reusable. The first stage of the rocket lands on Earth. Each first stage has a mass of 360,867 kilograms and provides 6,806,000 newtons while landing. What is the net force during landing? What is the acceleration of the first stage rocket during landing? Start by drawing a force diagram. There's my object. Gravity's pulling down. In order to be accelerating in the direction it needs to be accelerating, the applied force is a lot higher, so I'm going to draw a bigger magnitude. I know what my applied force is because it was given to me in the problem. I can calculate my gravitational force using the gravitational force formula, mass times 9.8. As assumed, the applied force is greater than the gravitational force. In order to find how much bigger, I need to find the net force. So I'm going to subtract the two to get my net force. Using my net force and Newton's second law, I can calculate the acceleration. I know my net force, so I can plug that in. I know my mass, so I can plug that in. And I can solve for my acceleration.